For the highlight of our program, our co-organizer, Jenann Ismael, has very graciously agreed to step in for a last-minute cancellation. So we're going to hear about how natural philosophy is really done here.
As he said, I'm just stepping in here. I would have never made it onto the program otherwise. First, I just want to say again, thank you to Bill Miller for everything he did, both to make this conference possible, but also just for making philosophy and physics so vibrant here at Hopkins. So we're sort of endlessly grateful. Also, because I know Sean isn't going to thank himself. This was really totally his brainchild, so you can blame him for everything that went wrong, but also thanks, Sean. So I'm going to speak really fast. There's this big picture sort of image of the universe that had a lot of currency in the 20th century of a universe of particles obeying deterministic laws. So Laplace gave us this sort of kind of shakeable image of a demon that knows the positions and the momenta of all of the particles of which the universe is composed. And as he says, embraces in a single formula everything that will ever happen over the history of the universe. So there's a lot of practical reasons that we won't ever have enough information to do this sort of calculation. And now, of course, we know the world is ultimately quantum, but it's still widely held that at least in that kind of setting, perfect prediction is possible. So what I'm going to do is I'm going to argue that that is wrong. I'm going to take this sort of simplest kind of deterministic setting and use it to bring into focus a kind of unpredictability that has nothing to do with indeterminism, nothing to do with ignorance. And I'm going to suggest that it's the crack in the edifice of determinism that life and cognition exploit. In fact, though, there's been a lot of themes in the conference that I think are going to connect in a natural way to what I'm saying. So this is a completely different way of making a point that Nima made in his talk, one that's often made in the quantum setting of the ultimate breakdown of the distinction between the system doing the observing or doing the measuring and the system that's being observed or measured. Except again, as I said, we're going to do it in a classical setting. And we're going to point out that that separation has always been partial and provisional simply because we're part of the world. And it has a funny way of reminding us of that. Also fortuitous in all kinds of ways that Thomas made such nice work of disposing of that sort of Archimedean view of the universe from the outside. As I said, it's sort of common to make this point in a quantum setting, as they both pointed out, but the snake of the serpent was always there, even in this classical setting where we mostly managed to keep it out of view. So since I'm a philosopher and since it's coming up on the end of the conference, so why not? We're also going to kind of suggestively point towards things like self-reference and free will and Gödel-type paradoxes. So here's a puzzle that you can think about in a purely mechanical way. So we have a theory, Newtonian mechanics, that says that a being, as I said, that knew all the positions and the momenta of the particles of which the universe is composed would be able to predict everything that would happen in the universe. And that, of course, kind of upsets our common sense conviction that if such a demon came up to you and told you that you will, for example, raise your hand in a second, you could just flip them off. And of course, so I was going to say, the same theory lets us construct a device. It can be just a little mechanical tabletop device that's designed to undermine any prediction that of what its behavior will be. So it wouldn't be hard to construct such a device. We're imagining just a simple kind of tabletop input-output machine that takes predictions of its output in a specified format and then does the opposite of what is predicted. So here's the puzzle. If there could be a demon of the kind that Laplace describes, we could chain it together with a device like this. We're going to allow the demon access to all physically accessible information. So we're going to imagine he has full access to information from the past, knowledge of the laws, unlimited computational abilities. We're going to let it make its calculation of the device's output, and then we're going to feed that into the device. So what would happen here? Or at least we can just at least ask, what does classical mechanics, which makes both of these devices possible, say would happen here? So this is a later version of a puzzle that comes from a paper by Michael Scrivens in 1965. And in the early version of the puzzle, we have a predictor and a counter-predictive device, but they're not actually communicating. They're sort of each performing their own calculation, and there's all of this discussion in the early paper in the literature that followed about who outcalculates who. And then in a 2010 paper, someone has the idea that what if we just let the predictor give the counter-predictive device its predictions? So when you do that, you don't have to worry at all about who outcalculates who or who calculates faster. Calculation is entirely irrelevant. The counter-predictive device just waits for the predictor to give its prediction, and then it does the opposite. So at this stage, it should be obvious, though, that to the demon, that the thing is rigged against him. He can predict that any prediction that he will make can be used to override his own prediction. That's the causal structure of the situation. So calculating isn't going to do him any good because his calculation will generate a piece of information that itself needs to be taken into account, and that will override the result of his existing calculation, and so on. So the demon is trying to make a prediction, but the prediction is connected to what happens, so that when he tries to do the computation, he's coming up against the fact that his prediction is going to affect what he predicts. And if you think about what the predictor is doing here, is effectively running a simulation of the evolution of the counter-predictive device in his head. So he's performing a calculation or evolving forward a kind of mental model of the world. He knows that the output of the simulation is going to feed into the device and prompt a counter-predictive response. So as soon as he finishes the simulation, he needs to redo the simulation with the new output, prompting a different simulation and different output, and so on. That is, his simulation has to include the results of his simulation. And if he thinks about this hard enough, the predictor knows in advance that he's never going to get ahead. Okay? Trying to get an accurate prediction of what the device does is chasing his own tail, chasing his own shadow. You would encounter the same problem if you tried to write a deterministic computer program that takes a prediction of its output and does the opposite. Again, you wrote the thing. So there's no missing information, and by stipulation, there's no indeterminism. And still, if you trust the program, there's nothing that you could learn that would overcome the difficulty. So what's going on here? So if you think about this in directly physical terms, it's at least prima facie puzzling. If the demon knows the initial conditions and it knows the laws, it should be able to use those to generate a prediction with certainty. And yet, he's faced with a situation in which he knows that any prediction he makes is going to be used against him. It's a losing game for him, and he knows that in advance. So you might be thinking, there's got to be ways of diffusing the problem by arguing that, look, there are practical, bordering on in-principle reasons that maybe a calculation like this wouldn't be physically implementable. Maybe it's impossible to know the initial conditions with perfect precision, impossible to carry out the computation in a practical way. But if all of those loopholes were closed, the structure of the thing looks really like a closed causal loop. And we can make that analogy explicit by realizing that advanced predictions of a Laplacian demon, that is an infallible predictor, would effectively be proxies, advanced proxies for the events themselves, since the demon predicts an event if and only if the event occurs. So making a prediction in advance is just like having the event in advance. And allowing it to cause its own defeat has the form of a closed causal loop. Okay. So this analogy makes it tempting to reason this way. Look, so long as this is a consistent world, the demon knows that he's done his calculation correctly. The counter-predictive device is going to have to end up doing what the demon predicts. And that, of course, is a conclusion that many people have drawn from determinism. They imagine when they're thinking about grandfather's paradoxes, for example, that you might imagine that you could sort of raise your arm in 5 seconds, even if the demon told you that you wouldn't. That is, if the demon told you you wouldn't, you could raise it. You could just thumb your nose at his prediction. But if you take this response seriously, you might think, unless he miscalculates, you're going to end up doing what he predicted. It'll be like death in Damascus. You'll try to avoid what you're told you're going to do, and your very efforts will somehow have to lead to affirming the prediction. Okay? So an intelligence that knew enough about the past could use the laws to calculate the future with certainty, you might think. And so we're simply not going to succeed in doing anything other than what a demon like this predicts. Okay. So while you're talking yourself into that kind of response, here's another puzzle. So imagine a universe with deterministic, effectively computable laws. Imagine a Turing machine inside that universe. We're going to give the Turing machine a database of past fact, and we're going to program it with the universe's laws. So it might seem here, if you think about this setup, though the Turing machine ought to be able to predict what any machine in its universe would do if it were given sufficient information about the initial state. But of course, we know it couldn't do that, because it could, if it could determine whether an arbitrary Turing machine would halt on a given input, we could use that to construct a machine that would halt if and only if it didn't halt. We would be able to solve the halting problem. This has the same structure, but an analogous, as the analogous solution that we were considering in the case of the demon predicting your behavior. Again, what do we make of this? So think about the setup here. We've got a Turing machine inside a universe with effectively computable laws, programmed with that universe's laws. Okay. We've given the thing a database of past fact. We know that in this case, the shortfall in its inability to predict isn't in determinism. So it's not that the laws aren't powerful enough to determine the future. And since the Turing machine is in a computable world, we know that if the laws are powerful enough to generate the future from an initial state, then the Turing machine is powerful enough to generate an answer from initial data. So again, what's going on here? You think about that one long enough, and you begin to see what's really going on. In fact, there's a perfectly general argument, independently of the physics, that there couldn't be a demon like this. There never could have been a demon of the kind that Laplace describes in the universe, not in classical mechanics, not in any theory. Here's the argument. So let's forget about demons for now. Let's just suppose we've got a system in the universe, maybe a computer. It's going to be our grand overarching database of fact about the world. The goal is to be able to put to it any question of physical fact about its universe, and the answer is going to appear in an output channel. Okay. Choose your language, as long as it's rich enough to describe every question of physical, answer every question of physical fact about the world. Choose the format of the question, and now all you have to do to find a question that it can't answer truthfully is ask, is the answer to the question that's about to be displayed in the output channel no? Okay. However it answers, it's going to be doing the opposite of what it says. The question of what appears in the output channel here, it's just a question of physical fact, and yet it can't answer truthfully. And notice that the problem is not a lack of information, nor is it indeterminism. And it's not just that you can't program this kind of computer to predict with certainty what it will do. Think about this. The system can't even accidentally guess the correct answer. Okay. Now think about this in purely mechanical terms. When you think about it in mechanical terms, it's clear what's going on. What's happening is that, of course, you all see it, by saying things, the computer is doing things, and we can get a kind of interference between what it says, that is the semantic content of its utterance or the way that it represents the world, and what it does, the act it performs in making the utterance. If one's dealing with a system that's in the business of representing the world, and the system falls under its own scope, everything that it does is going to cast a shadow at the semantic level in its representation or its simulation of the world. And every representational act, everything that it does, is itself an event in the world that it's representing. So there are going to be these kinds of interaction effects between what it's saying and what it's doing. And what we've done is we've set things up so that they interfere negatively with one another. That's what it means to say it can't do what it says. It can't say anything without doing the opposite of what it says. Okay. So in the case that we're describing here, the way that I'm going to put this is that computer can't stabilize the fact that the answer is meant to describe, that is the word that appears on the screen, independently of giving the answer. And again, the thing is set up so that no matter what answer it gives, what it will be saying will conflict with what it's doing. Okay? So this is what's going on in all cases of paradoxes of self-reference, and most of the semantic paradoxes. Okay? But there's no actual paradox here in the philosophical sense, because there are perfectly consistent ways that this world can be. The system can answer yes, it can answer no, it cannot answer at all. Those are all perfectly consistent ways that a world like this could be. It's just that whatever it does, it won't be speaking truly. So the right response to the puzzle here is that the system's theory of the world, its representation of the catalog of facts about the world, has to be incomplete. Incomplete, that is to say, on pain of inconsistency. In this case, not logical inconsistency, but inconsistency with what is the case. So this phenomenon, which I call interference, it just forces into the open the fact that representational activity is part of the world, and self-reference is just going to arise for a system in the world naturally and inevitably. And this was really what was behind that initial puzzle of the predictor and the counter-predictive device. It was the self-reference that the demon encountered when he tried to perform the calculation that sent him into that sort of paralyzing loop. Okay. Remember, he goes to calculate the output of the counter-predictive device, but he knows that the output of his calculation is going to feed into the device and prompt a counter response. So as soon as he finishes the calculation, he needs to run it again with that output, prompting a new response and a new calculation and a different output, and so on. Okay. So this fact, the fact that there's going to be these kinds of interference effects for a system representing the world from inside, is something that sort of gets pushed out of view in most day-to-day physics, because one is modeling other systems, so pendula, planets, gases. We maintain this sort of provisional separation of subject and object, or investigator and system being investigated. Even when we're modeling ourselves, we typically are not modeling our own current representational activity in real time. That is, we treat ourselves as sort of pushing ourselves into the frame and looking at ourselves from the outside. But interestingly, the people that have unavoidably encountered these effects are people that are, for example, trying to program an AI, an artificial general intelligence, in a robot or some kind of embedded agent. So they want to program the system with some general model, some general knowledge and the ability to model the world, and they're coming up against the fact that there are going to be problems of self-reference. Self-reference, of course, is usually thought of in these sorts of contexts as a pathology. You want to get as close as you can to minimizing the disturbances that the computer's own activity or the system's own activity has on the truth values of sentences in the field that it's representing. That's actually much harder to do than you might think. But look, interference is a familiar phenomenon in some domains. So an influential analyst predicts a fall in the value of a stock, prompting a sell-off. Polls in an election made public prompt strategic voting and affect the outcome. Anytime you have a prediction feeding into the domain that it predicts and affecting what happens in the domain, that's the phenomenon that I'm calling interference. So it's the paradox of predictability, the puzzle I started with, on a longer scale. Larger scale. Positive interference happens too. Positive interference is a self-fulfilling prophecy. A man's insecurity about keeping his commitment, shy lover drives her away, and of course, hilariously, the XKCD. So when you see things in this way, when you see the puzzles that arise naturally for a system that's representing the domain in which it's acting, there's nothing confusing about it. When you really naturalize representational activity, so you absorb it into the fabric of the universe, you see that it plays a role in what happens. You recognize that the possibility of these kinds of interaction effects was there all along. It was always going to be a delicate question how your own representational activity was going to affect what you were trying to represent. So there's a bunch of things that we can learn from this. So the first is that it brings into focus a kind of unpredictability that has nothing to do, again, with indeterminism and nothing to do with ignorance. This sort of unpredictability has connections, as I pointed out, to the halting problem and other paradoxes of self-reference. The second is that it corrects a misunderstanding of the implications of determinism. So this is the idea that gets expressed in worries about free will. The idea is that in a deterministic setting, it's just our ignorance of the past that makes us think that the future is open. That is, that a direct confrontation between a predictor without our mundane limitations on knowledge of the past would dispel that illusion. Okay. And what this does, I think it flips the script. Prediction is hostage to interference. The fact that an aspiring demon would have to keep his prediction hidden from you on pain of being overridden, right, makes the point that interference defeats prediction rather than the other way around. Interference is going to be an absolute limiting factor on prediction. So there's a physics question here about why classical mechanics, for example, doesn't in fact furnish the in-principle possibility of an embedded demon. So the quick answer in that case is that the light cone structure limits knowledge to the past light cone, which is never enough to compute anything that happens at any finite interval into the absolute future. But we know from the self-reference argument that no theory is going to tells you that there could be a system in the world that correctly answers all yes, no, and questions of fact about the world, could be right. So quite generally, the way that you should think of this is you take any set of consistent laws that allows the emergence of systems that can represent the world and use information to guide behavior. The laws will tell you where a system that's generating predictions is interacting with the environment in a way that's going to cause interference. But I want to spend the rest of the time just briefly emphasizing two very different types of lessons. So one is the thing that I said earlier, that interference is the crack in the edifice of determinism that life and cognition exploit. And the second one is that we live in the regime of interference. That is, our own experience of the world is organized around it. So the first, what all of this is really doing is bringing into focus the fact that representational activity, so gathering information, modeling the world, generating predictions, that kind of activity is tied up in the causal fabric of the world, and it makes a difference to what happens. That doesn't just mean that any system in the world that is doing these things will encounter interference as a kind of regrettable artifact of its embeddedness. The point is that that's what representational activity is for. So in philosophy, people often think about representation in a kind of detached way. There's the way things are on the one hand, and then there's our representations of them on the other. And that the goal of representation is truth, which is a kind of timeless relationship between the way things are and our representations. But as soon as you embed representation in the world, you realize that the mind isn't there to sort of passively represent. That sort of mind as the mirror of nature image of representation that Sandy pointed to as well. Its natural purpose, that is the natural purpose of representational activity, is interference, not truth. The representational machinery in your head is guiding action in a way that works to offset, counteract, thwart, obstruct, and otherwise get in the way of predictions that you don't like and promote the ones that you do. Okay. So think about three different types of systems engaging in paradigmatic behavior. So there's a rock rolling down a hill, magnetotactic bacteria. These are organelles that contain magnetic crystals that keep them oriented towards the sort of magnetic north, guiding the system's movements towards kind of the nutrient-rich environments that they need to survive. Or think about, for example, a frog snapping out its tongue at a passing fly. And then finally, think about a person making a decision. In the case of the rock, there's nothing of any special interest happening inside that system. In the case of the frog and the bacteria, by contrast, these are evolved systems. The internal machinery is using information to produce motor responses that allow the system to access free energy and do what it needs to offset the entropic tendencies that would otherwise lead to their dissolution. The logic of kind of anticipating the future and then selecting responses that would counter or offset what would otherwise happen and lead to a favored result for the system is implicit in the system's design in those cases. By the time you get to a person making a decision, the logic of anticipation and then selection of action, that's chosen to offset the tendencies that counter predictions it doesn't like, that's an explicit computation that the system itself is carrying out in real time. So we're running an internal simulation, right, that assesses the impact of different possible behaviors and then uses the output of that simulation to guide behavior into a preferred state. And it's crucial to this arrangement that the inner gears engage the outer machinery in a way that's designed to create counter-predictive interference. So remember, the problem arose for the demon because of the way that we harness the prediction to the thing that it predicts. In that case, this connection between the prediction and the thing that it predicts was contrived, and the relationship was adversarial. The predictor's goal was to thwart the prediction, and the counter-predictive device's goal was to foil, the counter-predictive device was to foil prediction. But if you ask yourself, what is a human mind? It's effectively a system that generates predictions chained together with a counter-predictive device. But here we replace prediction with the more general expectation. So predictions take the form of a probability distribution, where before we had two adversarial systems, one to predict and one to foil. What happens in the human mind is they work together, and the job of the system as a whole, unlike the pollster or the analyst, is not to achieve accuracy in its predictions, but rather a kind of selective inaccuracy. So the job of the responder is to curb predictions it doesn't like and promote ones that it does. So you think of the whole system as using what it knows to guide responses in a way that's strategically designed to shift downstream probabilities in a direction that it favors. So how does this work? Predictor uses information from the past to generate a probability distribution over futures compatible with what it knows. The predictor takes the distribution, conditionalizes on different choices, do X, do Y, and then makes a choice that, maximizes expected utility or whatever decision rule you favor here. So if you look at the structure of the computation here, what's happening is the system is hitting a conditional branch when it goes to predict its own computation-guided behavior in a way that opens up the space for multiple possible solutions, and then it chooses the one that it likes. So the responder is effectively using interference to sculpt the future by getting in the way of bad predictions and behind good ones. So our own perspective on the world is organized around, sorry about that, I don't know if you can see this, is organized around paradox of predictability type interference. If you're representing the world from within, and what you do is guided by what you know, you live in the regime of interference. Your expectations are meant to get in their own way. That's what they're for. So I think the native position of the embedded agent is rife with interference. I'm looking into my future in a way that's centered on the here and now, and I'm in the regime of the sculptor, not the predictor. So I'm going to close quickly by highlighting just a couple of little gestalt shifts that change, that this kind of thinking can induce when you're thinking about the role of intelligence in nature. So one was the idea that the natural purpose of representation isn't truth, but interference. Another is really leaning into the idea that life and cognition aren't incidental byproducts of the mindless crunching of physical law, but hacks that exploit the laws of physics to guide the flow of information and energy to their own ends. The third has to do, because I'm a philosopher, with this old familiar worry about free will. Okay? The idea still really has wide currency that determinism is supposed to reveal that your own sense of agency is illusory. So if you were faced with a Laplacian demon, the idea is supposed to be that knew enough about your past, it could predict what you would do and you would be powerless to do otherwise. So that's the death in Damascus vision, death in Damascus vision, that if the demon would predict that you would X and you would try your best to avoid doing X, your efforts themselves would lead you inevitably to Xing. What I've been arguing is that the opposite is true. An aspiring demon, again, is going to have to keep his prediction secret on pain of interference, or you can use it against him. So the real lesson there is not that avoidance is futile because prediction is possible, but that prediction is futile where avoidance is possible. Thank you.
Thank you so much, Jenann, for that amazing talk. And thank you, Jenann and Sean, for this incredible event and for having me here as a respondent. So I'm, unfortunately, as respondent, I totally agree with everything Jenann just said. So I will be sort of supplementing some of those considerations, trying to discuss some actionable steps forward for how this influences the landscape of mathematical modeling of complex systems. So indeed, forecasts have influence. Whenever the forecaster and the forecasted are in a common physical system, there's the possibility of these interference effects. The system modeler separation is clearly some kind of abstraction in many different situations, especially complex systems on the Earth system that are high dimensional and transfer information in a well-mixed way. And there are many, many examples that I'm going to go into a little bit of this. And I should say that also we live in an increasingly model-infused society, not only like within our minds, our internal models, but also many of the technologies we interface with are predictive and also influencing us. So as one example, as Jenann mentioned, here this is the forecast just before the 2016 US presidential election, which predicted many different organizations predicted Hillary Clinton had a very high chance of winning. This could have hypothetically affected the result by inducing voter complacency to some extent. However, actually determining whether that is the case is a little bit difficult, as I'll get back into in a second. Notice also on election day, though, the models happened to become correct. Once again, at around 6 p.m., they started turning around. So there's this concept of performativity, which is this notion of how descriptions of, in this case, linguistic descriptions can become realized as actual phenomena. So for instance, saying "I do" at a wedding is not just like description, but it's also the action of getting married. So this has been developed in various different settings. It was applied in the study of gender theory, and nowadays it's applied in some machine learning studies even. So there's also this other example, the financial markets, option pricing using the Black-Scholes equation, where in this book by Donald Mackenzie, he outlines how this type of financial modeling ended up sort of coming true in a lot of the financial markets. And he looked at many different instances of those models that are inducing self-fulfilling types of effects. So really, these real-world examples of interference truly abound. There's those examples. There's also pandemic forecasting, behavioral response to pandemic forecasts. There's content recommendations. There's planned behavior, climate forecasts, model-informed policy. And so it's truly a ubiquitous phenomenon in, at least on this complex system, the Earth system. And so I want to argue that there is a lack of a general theory about this system model interaction, this type of phenomenology. By model, I'm no longer referring to a fundamental set of equations of the universe, but I'm referring to modeling apparatuses that are applicable at the emergent scale. And so we're no longer talking about Laplace's demon, but we are talking about predictive phenomena. And by general theory, I don't mean some ultimate set of equations that are true. I mean a lot of words and concepts and philosophy and general understanding that could be formalized into equations. So in general, there's this picture, we have this model and the system, and they're occupying a common medium, and over time, we want to know what is it that will happen. So for instance, in the case of positive interference, over time, the system starts resembling the model. But there's also another effect that we're very familiar with, which is model inference or statistical inference learning, in which case the model over time starts to resemble the system. But generally speaking, there's a whole zoo of different possibilities, and they demand a wide set of advances in theory, both from the philosophical side and the scientific side, using both words and equations. So what should a general terminology or language of this type of interference behavior include? I would suggest it should involve some way of putting the model and the system on the same footing so that you can compare model predictions to behavioral outcomes. Have some notion of distance or similarity between the model and the system. Allow characterization of the structure and dynamics so you can trace whether a model and system over time are coming together or moving apart. And structure, meaning it's a relatively descriptive, rich description, potentially. And be formalizable in terms of mathematical equations and mathematical techniques, but not overly restrictive. And there is definitely a risk of over-formalizing and jumping into one particular mathematical framework and then landing in the wrong basin of attraction because of that. So I'm going to talk about one example way to formalize this type of notion. So it's through the language of probability distributions. So here I'm depicting what's called the probability simplex, which is the space of probability distributions for a given set of outcomes. You see these three different possibilities, A, B, and C. Their probabilities add up to 1, and they're all within 0, between 0 and 1, and so they form this triangular region, which we can then look at in and of itself, and each point within this triangle represents a probability distribution. So, for instance, in this case, we could have the model and the system both be individual points within this probability simplex. On the probability simplex, there are well-defined notions of distance, things like the Fisher information metric, and distance-like things such as Jensen-Shannon divergence, callback-Leibler divergence. And we can track dynamical trajectories on the simplex as well. So I just want to discuss briefly a class of phenomena, system model convergence phenomena, where this distance is decreasing with time. So we've already discussed this notion of positive interference or model performativity, where the system is pulled towards the model. That's often when it's the system exhibiting its own response, but we can also talk about feedback control systems where there's intentionality on behalf of the modeler, on the part of the modeler, in terms of trying to bring the system into alignment with the model. There's also cases where the model moves towards the system. Things like statistical inference, where you're trying to infer what is the appropriate model of the system, but also something like natural selection, if you think about organisms as encoding certain models of their environment, then over time the selection process will lead to more accurate models. But you can also have both of these points in the probability simplex moving around, such as in evolutionary arms races, where you have, say, the surface proteins on some cell that are evolving so as to not be properly modeled by a particular virus, which in turn is evolving and maybe evolving faster so as to catch up with the system. And in general, this system here, this is actually the case of negative interference, where the system is moving away from the model. Yet you could still have model system convergence if the model is catching up fast enough. Yet also another important case is that we often do what we're predicted to do. Recommender systems, things like friend suggestions, product suggestions, content recommendations, they tend to move us a little bit towards the model of us in addition to learning about us. And so another example is in the case of text corpora, where large language models are going to be spewing out all kinds of language, and that language will then be used to train next generations of large language models. So I was going to talk about a couple of technical challenges, but I'd just like to say there are many, and they can be, well, some of them are inference of interference, when we actually can make up a model or meta model of the model and the system and their interactions. And then we could potentially observe a model and a system interacting over time and then infer things about it and try to figure out what are the actual interference effects that are going on. In general, it may be difficult to discern whether the interference is at play or not. Also, I wanted to mention the notion of a consistent estimator in statistics needs to be refined a little bit when the actual estimate that you have of the system influences the ground truth of the system. And even things like Bayes updating will not necessarily be optimal in a setting where the environment responds. And so lastly, I just wanted to say that inference is easier in the case of positive interference, because you have a system that's acting to validate the model, and inference is harder in the presence of negative interference because you have a system that is evading the model. So in summary, interference is ubiquitous and significant. We lack a general theory and taxonomy, and there was one example of how to potentially formalize it using the language of probability distributions, and there are many interesting, tricky technical challenges. So thank you very much.